All right, in this second part of D3, which is dealing with exponential functions, we're going to talk about different applications of exponential functions. All right, so just to get us started, when we talk about exponential models or exponential functions and application problems, remember that what we have is we have our basic formula, which is going to be f of x equals a times b to the x. Now, when we talk about this from application standpoint, we still need to find a and b. And so the first thing that we're going to talk about is the base multiplier. This is our b value. And when we talk about what number we're going to pick for b, what we're looking for is phrases like double, triple, quadruple, factor of. Anything like that implies that we are multiplying continuously. The second variable that we have, or the second value that we need, is the initial value. And remember, this is the number that we're going to have in the front. All right, so we're just going to look at a basic example of an exponential model to start us off with. When we come to our first example, we have the number of centenarians, people who are 100 years or old or more in India, is projected to increase by a factor of 1.04 each year after 2010 until 2100. All right, so let's go ahead and just start with this sentence. So it says that it is projected to increase by a factor of 1.04. Because we have that phrase, factor of, this is my base multiplier. So what we have is b equals 1.04. And that's all that sentence gives us. All right, now when we come down to part A, it says if there were 50,000 centenarians in 2010, then we want to go ahead and write our function that gives this number x years after 2010. And remember, that's our starting value. And so this is going to be our a value. All right, I don't think I left enough room here, so we're going to go ahead and try to write this again. All right, so what we get is f of x equals, we have our initial value, we have our base multiplier, and so this is going to be 50,000 times 1.04 raised to the x. All right, the second thing that we want to do at this point is we're just going to estimate the projected number of centenarians in 2050. And so 2050, this is 40 years after 2010. So x is going to be 40. All right, so if we go ahead and plug this in, we get 50,000 times 1.04 raised to the 40. And from here, this is a calculator problem. When I plug this into my calculator, I get 240,000 0.051, and I do get 0.03, but because we are talking people, we are going to go ahead and round, and so this is just going to be 0.51. And if you want, you can put people, or more specifically, these are centenarians. All right, this is our basic example. Now, exponential models, just like we have lots of classic examples of linear functions, we also have some classic examples of exponential functions. And so the first ones that we are going to talk about is compound interest formulas. Now, depending on how many years you've been taking classes at DACC, one of the first ones that we talk about is simple interest. And simple interest is basically that. It's the simple interest formula. When we talk about compound interest formulas, we do have several versions of this. The first thing that we have is compounded annually. And when we talk about compoundings, this is how many times per year do they apply the interest rate formulas. So when we talk about compounded annually, it's only compounded once at the end of each year. Our formula for this is A equals P times 1 plus R raised to the T. Our other compound interest is going to be used if we compound several times a year, and it can vary depending on how many times per year we're going to compound. But basically what we're going to do is we're going to take our compound annual formula, and instead of doing 1 plus R, we're going to do 1 plus R over N. And we are going to change our exponent from just a t to an nt. And I'll explain what all these variables mean in a minute. And then the last one we have is continuous compounding. Basically, it's what it says. Every time you sign into your bank account, it's been compounded, and it continues to compound. There's no set number of times. It's always happening. And this one, we do have a different formula. This is A equals P-E, R to the T. And E is a number. It's like pi. Some people like to remember this by PERT. A equals PERT, whatever it takes. Just so you know, you are not required to memorize these formulas at this time. They will be provided to you. All right, so now let's talk about what all of these letters represent. Okay, the first one we have, A. This is the amount in the account at whatever time that we're looking at it. Okay, now this is not in the right place. That should be over here with the P. This is principal. And the principal, what this represents, is the original amount in the account. How much did we invest? How much did we borrow? Whatever it is. All right, we also have R's in all of these. So notice A, P, R, these are in all of our formulas, and R represents our interest rate. This is one that we do have to be careful with. We do need to make sure that we express it as a decimal. Most of the time it's going to be given to us as a percentage. And remember, in order to turn a percentage into a decimal, we move our decimal point 2 units to the left. All right, the other one that everyone has in common is t. And so t is going to be time, and we also need to be careful with this. It is going to be time in years. So every now and then you'll see an example where we're just doing this for months. And if it's months, we do need to go ahead and convert that into years by dividing by 12. All right, the last thing we need to talk about is n. And so n is, we have set values for n. And so n represents the number of compoundings per year. And so, for example, if we have semi-annually, this is twice per year. And so n equals 2. Quarterly, this means that we're doing it 4 times. And so n equals 4. Monthly, well, there's 12 months in a year, and so this is going to be n equals 12. And then finally, the last one we have is daily. And there are 365 days per year. And so for this one, n would be 365. All right, last thing that I do want to mention is let's talk about that number e again. As I mentioned, e is a number similar to pi, okay? It is an irrational number that is approximately 2.71828182846, and it keeps going, and it has no set pattern. In future math classes, you will talk about, okay, where does this number come from? But for now, we're just going to try to figure out where do we find it on our calculator. And if you go on your calculator, you should see a button that says LN. This stands for natural log. And it's going to be one of the options above that. So if you press second LN, you will go ahead and pull up the number E. Unlike pi, where we are required to memorize at least the first 3.14, we are not going to be required to remember E at all. And I will tell you that, me personally, I know that it's 2 point something. That's it. Okay. In terms of what is this number used for, just so before we get into it, this is a number that appears a lot in examples in nature in terms of exponential growth and decay. And so we're going to see it quite a bit in the examples that we're going to look at now, and we're going to see it as we continue through the rest of this module. All right, let's go ahead and start looking at some examples. All right, so in these examples, the first thing that we want to do is we want to figure out which formula we want to use. And then basically we just need to plug in the information. So for example A, the first thing that I want to look for is what kind of compounding are we doing? Here, okay, granted I misspelled it, but it says that we are compounding annual, and that should be annually. So what that means is the formula that we want to use is we want to use A equals P times 1 plus R raised to the T. After that, we want to figure out what are the numbers that we're given. So up here we have principal is 2,000. That is going to be my p-value. We have next our interest rate is 8%. And remember that we do want to convert this to a decimal. And so we are going to move our decimal point 2 places to the left. And we should get 0.08. And the last thing that we need is we need our t value. And so it says here we want to know the balance after 4 years. And so what we get is t is equal to 4. All right, we want to go ahead and plug these in. And if we plug these in, we get 2,000 times 1.08 raised to the 4. This is now a calculator problem, and so when we plug this in, let me back up a little bit. We have 1 plus 0.08 raised to the 4. I do recommend doing some simplifications. You don't have to do a whole lot, but anything that you can do by hand makes plugging this into our calculator easier. So I'm going to go ahead and add the 1 and the 0.08. And then from here, when we plug this in our calculator, we're basically going to plug it in just the way it is. The only thing that we need to do is we do need to use our caret key, and we want to raise this to the 4th. Now, one of the things you do want to be careful about is if you are one that you kind of do one thing at a time, that's perfectly fine. Just make sure that you are using the second answer key on your calculator. And I'm going to show you kind of what happens if we don't. So if I plug this in, the whole thing that I have here, what I get is 2720.98. And so we do one around to the nearest thousand, or sorry, the 100th, because we are talking money. Okay, so now, as I said, you do want to be careful when you put this in your calculator. Some people, what they like to do is they like to say, okay, well, what is 1.08 raised to the 4th? And what I get here is I get 1.36, and this is a rounded value. Now we do have to be careful because when we multiply this by 2,000, what I get is 2720. And you may think that's not a huge difference, but when we talk about the computer program where we're doing our homework, they are going to care about $1. That, that's actually probably something that you really want if it's your bank account. You want every penny you can have. So what we call this is called intermediate rounding. And this is something you do not want to do. If you are going to do this, if you're going to do just one thing at a time, on your calculator, what you want to do, instead of typing in the 1.36, is above the negative button, you should see something that says answer. And so if you press the second negative button, what it will say is 2,000 times answer. This is something that you should use if you're going to be doing this one thing at a time. And what this does is it basically takes whatever the previous answer is and plugs it in. And so, for instance, instead of doing 2,000 times 1.36 and typing it out, what it's doing is it is doing 2,000 times 1.3036048896, and I don't know if it keeps going, it probably does. If you do it this way, then what you should get is 2720.98. Now, one of the things, if you are using the second answer feature on your calculator, just note, if you make a mistake, you do have to go back and do this from the very beginning. All right, let's go ahead and look at a couple other problems. All right, so this is our first one, the compounded annually. This is our most basic. Okay, now we're going to go ahead and talk about another compounding. We're going to look at two. All right, so the first one we have, we're going to do part A. And part A says that we want to compound semi-annually. This is the first thing I want to look at. I'm not going to look at anything else until I figure out what's the formula that we need. Okay, so now that we know the formula we need, we can go ahead and figure out what everything is. So for part A, we have P is equal to 1,000. Because we are compounding semi-annually, we do want our second formula, which is P times 1 plus R over N raised to the NT. All right, we have P is 1,000. We have R is going to be 0.12 because we want to make sure that we convert it to a decimal. And we have T is equal to 20. All right, so if we go ahead and plug this in, and we need one more thing. We need to know N. N is, we're compounding semi-annually. That means twice a year. And so N is going to be 2. All right, if we start plugging this in, we get 1,000 times 1 plus. We have R is 0.12 over 2 raised to the 2 times 20. Again, I do want to go ahead and simplify some of this stuff. I'm going to leave the 1,000 alone, but I am going to go ahead and simplify the inside. If we divide 0.12 by 2, we get 0.06. And if I add that onto 1, we get 1.06. I can also simplify my exponent, and if we simplify this, we get 2 times 20 is 40. So now we can go ahead and plug this in our calculator. And what I get is $10,285.72. All right, that is part A. Okay, now we're going to go ahead and look at part B. And the only thing that we're going to change is our compoundings. So for part B, we want to change this to monthly. And so what we have here is we still have P is equal to 1,000. We still have R is equal to 0.12. We still have T is equal to 20. And this one, if we're going to be compounding monthly, that means that we are going to be compounding 12 times per year. And so let's see what happens when we look at this one. All right, if we plug into our formula again, we get A equals 1,000 times 1 plus 0.12 over 12 raised to the 12 times 20. All right, when we simplify this, I'm going to start with inside the parentheses. If we divide 0.12 by 12, we get 0.01. And so if we add that onto 1, we get 1.01. And if we multiply 12 times 20, we get 240. All right, we're going to go ahead and bring up our calculator. And let's see what we get here. This time, I get 10,892.55. And so notice here that what we get is we get about $600 extra just by increasing the number of compoundings. Okay, that is practice with our compound interest formula for compounding multiple times per year. The next one we're going to look at is we're going to talk about the compounded continuously. All right, here we have our compounded continuously, so this means we do need our last formula. And our last formula is A equals P-E-R-T, or P times E raised to the RT. All right, we are going to go ahead and plug in our information. So we have P is equal to 1,000. We have R is equal to 0.12. Again, we have to rewrite it as a decimal. And we have our time is going to be 45 years. All right, so when we plug this in, we get A equals 1,000 times E to the 0.12 times 45. Again, I'm going to go ahead and simplify what I can. And so if we multiply 0.12 times 45, I believe that we get 5.4. All right, we're going to go ahead and finish solving this off. So if you're using a graphing calculator or any TI calculator, if you look over on the left side of your options, you should see somewhere you have your x squared, and on mine below x squared I have log, and then I have ln underneath that. And so to get the E, what we're going to press is second ln, and then it's going to go ahead and pull up our E. All right, when I do this, I get 221,406.42. We're going to round up. And we're done. Now, for all of these, a lot of what we're doing is we're comparing the same dollar amounts and the same rates. And one of the things to note is in the homework, some of the problems are going to ask you to figure out what would be better. Compounding continuously at a smaller interest rate, or compounding quarterly or monthly or something like that at a higher interest rate. And it really boils down to you have to figure out which one is actually going to be better. You would think higher interest rate might be better, but continuous compounding does increase faster. And so even though it's not always the case, you do have to consider both of these when you think about where to invest your money and how often are they compounding. Higher interest rate is not always going to be the better option. All right, let's go ahead. This is kind of one of our classic examples when we talk about exponential models. And now we're going to look at a couple other ones. All right, the last classic examples that we're going to look at is exponential growth and decay. Basically, one of the things to consider is, I know that we've seen lots of different formulas, but this one is very similar to our continuous compounding formula. The only thing is we're going to be changing a couple of the letters. So when we look at this formula, what we have here is instead of a principal, which is the original dollar amount, we're replacing it with a sub 0, which is the same thing. A sub 0 is the original amount. The amount at time t equals 0. And so the only difference is that it's not a money amount. It can be anything. The other thing that we're going to replace in our formula is instead of R, which was our interest rate, is we're just going to replace it with a constant. This is going to be the formula that we use for exponential growth and or decay. And so the thing to keep in mind is that we have two different possibilities. If k is greater than 0, then we call it an exponential growth formula. If k is less than 0, then it is an exponential decay formula. And we talked a little bit about this last time when we talked about graphing exponential equations. If it's e is a number larger than 1, and if it is a positive exponent, then it is going to be growing. If it's a negative exponent, it is going to be decreasing. And so that's the difference between these two. All right, so those are going to be the numbers that we work with. Now, some examples of when we use this formula. Quite often when we talk about bacteria populations and the growth of bacteria populations, we use the exponential growth formula. The other example where we see this is when we talk about half-life of radioactive substances. For instance, when we're trying to figure out how old a fossil is, we use radioactive isotopes, and we set up our exponential decay model that way. In this class, just so you know, we are not going to discuss how to find k algebraically. This is going to be a number that's automatically given to us. But when we get into the next math class, pre-calculus, we will talk about how to find k algebraically. All right, let's go ahead and look at a couple of examples. All right, the first one we have is in a study, E. coli bacteria were found to be capable of doubling in number about every 49.5 minutes. The number of bacteria after t minutes can be modeled by the formula n of t equals n sub 0 times e raised to the 0.014 t. All right, so for this, we want to go ahead and suppose that n sub 0 is 500,000. This is the initial number of bacteria per milliliter. We're going to go ahead and compute how many bacteria are present after 99 minutes. So let's go ahead and see what we can do here. The first thing that we're going to do is, notice here it does say verify using a calculator. Okay, what that means is we are going to go ahead and start with our 500,000. I'll get this to work right. Okay, after 49.5 minutes, we say it doubles. And so what we are going to get is 1 million. All right, if we add 49.5 onto this, then what we get is 99 minutes. And it's supposed to double again. And so after 99 minutes, we should be at 2 million bacteria. All right, so now let's go ahead and use our formula. So if we do this, we get N of 99 equals 500,000 times E to the 0.014 times 99. All right, I'm going to go ahead and simplify the exponent. If we do that, we get 1.386. And we want to go ahead and plug this in our calculator now. When I plug this in my calculator, I get 1,99411.36. And this is 1,999,000. And so that's pretty accurate. Remember, it says about every 49.5 minutes. And so our formula is accurate. All right, the next thing that we want to do is we want to determine graphically how long it takes for there to be 25 million bacteria. Okay, now we're going to go ahead and basically this is the formula that we want to set up. 25 million equals 500,000 e to the 0.014 t. All right, so in order to do this, what I'm going to go ahead and do is I'm going to go ahead and put the right side into my calculator, my graphing calculator. And I'm going to put the second number in for my Y2. All right, so here's my graphing calculator. For the first one, I'm going to go ahead and put in my 500,000 E, which is right above my LN, and I'm going to go 0.014x and press enter. The second one, I'm going to put in 25 million. And then I do want to go ahead and go to my window. I'm going to leave my x's alone for now. But I am going to go ahead and come down here. I'm going to change my y min to 0. And I'm going to change my y max. This is how far up I want to go. I'm going to change it to 40 million. let's go ahead and change our x's as well. And so let's see here. Let's try 100 and see. No, I don't even think we need to go that high. I'm going to try 50. We're going to play around with it because I don't know the answer. And so if we go to our graph, what's wrong with this? Okay, let's try it again. All right, we need to go out a little further. And so I'm going to go to my window. I'm going to go out to about 100. Let's go out to 200. I'll try 1,000. Just because, remember, at 99 minutes, it's just doubled or quadrupled, and so we do need to go out a little bit further. Okay, let's try it now. All right, there we go. Okay, so now we want to go ahead and calculate something. If you come here above trace, you will see that there's that calc up there, so we're going to click on that. And I want to click on intersect. We're going to go ahead and use our left and right arrows, and we are going to try to move our cursor over near our graph. Okay, now I can see my cursor. And I want to try to get it as close as possible to this intersection. If we press enter, enter, enter on the guess, and as soon as it comes up with our intersection, we're done. And so here we have that our intersection try that again. We have that this intersects at 279. And so that is going to be our answer. T equals 279 minutes. All right, so when you think about that, that is basically a little over 4 hours in order for you to have 25 million bacteria per milliliter. All right, so that takes care of this one. Now, as we move forward in this module, we will be talking about other ways to solve these equations that are going to be algebraic, that are not going to be using calculators. But we have to talk about logarithms before we do that. All right, we have one more example that we're going to look at. Now, we're going to talk about half-life. And so one of the things is that on this, you can go ahead and create a formula using E for half-life, but we can also do this in terms of 1/2, okay? And so what we're going to do is we are going to have our formula A of t equals c times 1/2 raised to the t divided by k. Again, this is not a formula you need to memorize. We're just going to go ahead and plug in. All right, so we have links on Facebook typically have a half-life of 3 hours. So after 3 hours, half the people are engaging with that particular link. We want to determine a model that estimates the percentage of engagements after t hours. And then we're going to use that in order to estimate the percentage after 4 hours. To get us started, we don't have an original amount, and so we are looking at percentages. And so we're going to start with C is 100%. It does not matter if we convert this to a decimal. We don't have to. We can leave it just like this. We have t is equal to nothing at the moment, but it will be 4 in a few seconds. Okay. And we have k is equal to 3. All right, the first thing we want is our model. For our model, we're not going to plug in the 4 for the t. But what we get is c equals 100. A equals 100 times 1/2 raised to the t divided by 3. That is going to be our model. All right, from here, we want to go ahead and plug in our value for t, and we get a equals 100. If you want, you can write this as a decimal. It does not matter. Raised to the 4/3. All right, so if we go ahead and do this, what I get is 39.69%. And depending on how it wants it to be rounded, you may want to round that to 40%. Okay, so now real fast, why did I say that we don't have to convert to a decimal on this one, whereas on all my other problems I emphasized it does have to be a decimal? And this one is because no matter what here, these two numbers are the same types of values. And so, for instance, assume that 100% as its original amount. You can also convert that into assume it has original 100 engagements initially. Because if we do convert it to a decimal, well then our final answer is going to be 0.3969. And then we have to convert that back to a percent. And so all we're doing is we're kind of just taking a little bit of a shortcut in order to skip the convert one way and then have to convert it back. Okay. All right. And one of the things when we talk about the half-life, we really don't have to know what the original amount is for most of these. We can talk in terms of percentages. All right, let's look at one more. Last one we have is radioactive carbon-14, which is found in all living things, has a half-life of 57 years and can be used to date fossils. Suppose a fossil contains 5% of the amount of carbon-14 that the organism contained when it was alive, and we want to estimate the age of the fossil, and again, we're going to do it graphically. Okay, so we want to set up our formulas again. Okay, so we have A of t. Again, it originally had 100%, and so we're going to use 100 again. We have 1/2, and then we want to do t divided by 5,700. We are going to plug in 5, which is our 5% for our A of t. And this is what we're going to go ahead and plug into our calculator. All right, so let's go ahead and bring up a calculator again. Okay, we're going to go into our y equals. we're going to plug in (100) times 0.5 raised to the x divided by 5700. Alright, for my y1, we're going to plug in 5. And we want to go ahead and extend out our x's. Let's see what happens. I'm just going to go to the table. To be honest with you, that's what I want to do. Okay, let's see what we got here. Alright, I'm going to change my table setup. I'm going to start at 0. I'm going to go by 1000 to try to get us a little bit closer. Alright, we are looking at about 24,000. And so I'm going to go ahead and go back to my table setup. I'm going to start at 24,000. So I'm going to use that to create my window. So for my X max, I want to change this to 25,000. I'm going to change my Y min to 0 and my Y max to 100. Alright, if we graph this, this is what it basically looks like. Okay, if you want, you can go ahead and zoom in on the window. I'm going to go ahead and change my Y max to 50. Not enough. Okay. Okay, that's about as good as we're going to be able to get it. So I changed my X max to 40,000, and I changed my Y max to 50. And then we're going to go ahead and calculate again. So we're calculating an intersect. Again, I want to get as close as I can to it, and I think I lost it. That's about as close as I'm going to be able to get. We press enter, 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 and when we do that, we get 24,635. And so that is going to be my answer. T equals 24,635 years. All right, and so that is some examples of exponential decay. Okay, all right, that finishes off this section. In the next section, we're going to be talking about logarithms and their relationship to exponentials. All right, thank you.